speak about spatio-temporal analysis and directions for future research. So I want to acknowledge the students Nitin, Arvind, Vishnu, Manikandan, Samadan and Krishna, and also the funding from Department of Science and Technology, ONR Global, Tango, which was the earlier project before POCA, run by Maria and IIT Madras. So this is a picture of a Holter monitor. This measures the heartbeat for a long time and then does a lot of analysis. So this is so in medical field or in physiology, the complex system approach is very popular, and they are used successfully to develop many instruments. And it's really commercialized and so on. And work has been mostly done by physicists and mathematicians, and electrical engineers and so on. So I think that's a good example to emulate. So in the first part of the talk, I spoke about time series analysis. Now I'll speak about spatio-temporal analysis, and I will end with some directions for future research. So just a small recap of what I did in the morning. So what I said was that combustion noise is really not noise, it is deterministic chaos. And in turbulent combustors, and I'm speaking only about turbulent combustors, the stable operation, the time will be a periodic low amplitude fluctuations, which we call combustion noise. Again, it's chaos, high dimensional chaos. Normally physicists call like dimension of 5 or 6 as hyper chaos, but our dimension is like 12, 14 or something, so it's really high dimension. And then we go through the state of intermittency, where there is a periodic epochs and periodic epochs, interspace between the periodic epochs, and then we go to combustion stability. And I just want to emphatically say that intermittency presages the onset of thermoacoustic instability. This has been there also. I've seen some signals when I was a student, graduate student, but nobody had quantified the signals till the last 5 years or 6 years or so. And this is the path which you take combustion noise via intermittency to full-blown instability or periodic oscillations. And I also mentioned that during the stable operation, we have desynchronized chaos, and then we go through the state of intermittent phase synchronization, then we go to phase synchronization, and then we go to generalized synchronization. This first picture would be the stable operation, the second picture would be intermittency, third one, and fourth one, both are limit cycles. The first you have low amplitude weakly correlated limit cycle, and then which corresponds to phase synchronization, and generalized synchronization gives strongly correlated limit cycle. So once again, to summarize, we go from desynchronized chaos via intermittent phase synchronization to phase synchronization to generalized synchronization. So now I want to look at the spatio-temporal picture. So we want to look at the phase between heat release rate and pressure. We know from Rayleigh criteria that it is the phase that determines whether we have driving or whether we have damping. So if the heat release rate and pressure are in phase, we have acoustic driving, and if they are out of phase, we have acoustic damping. So what we do is to take an image and look at the, so imagine there is an image here, and if there is a heat release signal, each of the pixel will have, if you are taking high-speed images, will have a time series. So if you now take a pixel of heat release rate and find the phase with the pressure signal, and then you can mark it with color. And so we see that during combustion noise, the phase between heat release and pressure, they are having a grainy structure, so they are really there's no correlation. And during thermoacoustic instability, they are well correlated. And during intermittency, during the periodic part, they are really having a grainy pattern. During the periodic part, they are very well correlated. So if you plot the phases as phasors, and then you have during the stable operation, you have phasors which are randomly oriented, and during thermoacoustic instability, the phasors are all lined up, which means aligned. During the intermittent state, you have simultaneous coexistence of regions where the phase is aligned and regions where the phase is not aligned. So if you look at the first picture and last picture, if those of you have studied paramagnetic to ferromagnetic transition, you would have seen such a picture. Now we have a picture in between where you have both the coexistence of stable and unstable regions. So here the phases are aligned and here the phases are not aligned, and such a state is called a chimera state. So chimera was discovered in 2002 actually in a collection of oscillators. It was found by Kuramoto and Batoto that you can have simultaneously regions that are synchronized and then regions that are desynchronized coexisting together. And this fancy name, chimera, was given by Abrams and Strogatz in 2004. So it's a very recent field, and we are having this chimera-like structure in the heat release rate field during intermittency. And the regions of disordered and ordered phases change their location with time, and this the physicists call breathing chimera. Now, the transition from phase asynchrony to phase synchrony, this is phase asynchrony, so the phases are spread all over the place, and this is thermoacoustic instability, so the phases are nearly uniform, and this is intermittency where there's regions of in-phase regions and then phases were scattered all over the place. So this is the way physicists represent, one way physicists represent chimera, the other way is with the arrow points. So we go from disordered and incoherent dynamics to ordered and coherent dynamics through this chimera state, and we actually get some kind of pattern formation during this. So we know that thermoacoustic instability is caused by positive feedback between acoustic and unsteady heat release rate. But in the statement, something that is often not emphasized is the role of hydrodynamics. Hydrodynamics plays a very big role, and I see that Yanis has given a talk right before my talk on the role of hydrodynamics. So we will see that from a complex system perspective. So the coupling is spatio-temporal, since the flame is not compact, but the flame is spatially extended. That means all parts of the flame need not necessarily, actually will not in a turbulent combustor behave the same way. And there is a very nice reactive hydrodynamic flow field there, and that contributes big time to the instability. And I missed the previous talk. I'm hoping to see the recording, but that's a very important thing. So intermittency in the time domain is a gradual emergence of spatial patterns, of temporal patterns en route to thermoacoustic instability. So here is a very disordered pattern, and you go towards very ordered pattern through regions where pockets of order and disorder coexist. So the left side is pressure and the right side is heat release rate. Now, a pattern is indeed repeated arrangements. You can have repeated arrangements in space and time, and patterns are ubiquitous in nature, and you can see very nice patterns in fish and zebra. And this is Belisov, Sapolsky, what's popularly called BZ reaction. So are there patterns in turbulent thermoacoustic systems? So if you look at the P prime, Q prime, that is acoustic driving, this is during the occurrence of stable operation of combustion units, and the black line is the acoustic pressure and red is the heat release rate, and you can see that they are not so coherent and it's grainy structure, and the coherence is very short duration, short length coherence only. No coherence over mid-length space. Now, if you look at the intermittency, again you see incoherence during the periodic dynamics, but when we go to periodic dynamics, you can see the emergence of coherence. And when you go to thermoacoustic instability, you see really big regions of spatial coherence. They increase in size and also strength during thermoacoustic instability. So I'll play this movie, I hope it plays there. So you can see that there is disordered emergence of small scale vortices occurring during the flow field during combustion noise. This is actually a bee scattering picture. We see that the airline with oil droplets, and we can see so the oil burns across the flame, so there is a boundary. Now, if you look at thermoacoustic instability, so you can see that now you see large structures, and the small structures are organizing themselves. Large structures, you can see, is composed of these small structures, and is being repeated. So this to illustrate this, after viewing this picture for a long time, we've drawn a cartoon. So during the stable operation, the small scale structures, they don't roll up into any large structure, whereas during thermoacoustic instability, there's self-organization. There's a collective interaction that causes the organization of this small scales into large scale. So it's not that the small scales are disappearing, but they're getting self-organized to form large scale structure. So we can plot a bifurcation diagram between the RMS value of pressure and the equivalence ratio. So we start from here. The combustor is near stoichiometric, and we go left, and then at this point we get thermoacoustic instability. And corresponding to each point, you can see different patterns. So the stable operation, which is occurring at stoichiometry, is having one kind of pattern, that is a highly disordered pattern. And then during intermittency, there is this alternate occurrence of periodic and periodic patterns. And then you see during thermoacoustic instability very strong coherent pattern. So the onset of thermoacoustic instability is indeed the onset of a pattern formation. Just the way this is studying relay Madras convection and all that, this also can be studied in the framework of pattern formation. And so there is hydrodynamics, acoustic field, and flame. So normally in all the pictures, they say there's a feedback between acoustics and flame, but this hydrodynamics is very important in reacting to hydrodynamics. So hydrodynamics and flame really go together, and there is a intertwined and highly intricate interaction between the wide spatio-temporal scales in the flame, because hydrodynamics are lot of scales, small scale to large scale, flow and acoustics, and this happens through pattern formation. So thermoacoustic instability is indeed the result of coupling between hydrodynamic, flame, and acoustic field, and this coupling is happening through the pattern formation. Again, the coupling causes the pattern formation, and the pattern formation reinforces the coupling. So this is a very interesting way. And in physics, instabilities are looked at through the eyes of pattern formation, and I think it's very interesting because once you know how the pattern is formed, we could perhaps disrupt the pattern and stop the instability. So now I want to talk about fractals in space. We saw fractals in time in the earlier talk, but what happened to space? We saw that the signals were highly multifractal during the stable operation, but they went to highly periodic signals during unstable operation. So did this fractal structure of the plane, was it lost, or is it still there and something has happened? Because we know that planes have a fractal structure as they are. Turbulent planes have fractal structure. Now, we saw in the morning that from stable operation of combustion noise, when you go to combustion stability, this broad multifractal spectrum collapses to a point that is we observe a loss of multifractality in pressure oscillations at the onset of thermoacoustic instability. So is there multifractality in turbulent flame topology, and what happens at the onset of instability? So we certainly observe fractals in the frame topology during all the way during this transition. So you can see that there's a cartoon. The large structure is comprised of small structures, and if you zoom in, you can see small structure within the resolution of the experimental recording device. So we want to examine how the large coherent structure forms during thermoacoustic instability using this concept of fractal. So we take this image and find the contours, and then we find the multifractal spectrum corresponding to this spatial image. Earlier we were doing temporal image, and now we are doing spatial image. I'm not going into the details, but we're using box counting method and multifactorial analysis of the flame dynamics we'll be doing during transition to instability. So first we look at combustion noise. We see small scale structures that are present along the shear ledge during the occurrence of combustion noise. And so you see small wrinkles. And so if you look at the capacity dimension, it has a value of close to 1.3. That's the value reported in the literature for steady flames, turbulent flames. And this is the most dominant singularity, which is corresponding to the peak of the multifactorial spectrum. And this is how the multifactorial spectrum itself looks like. So nothing fancy here as expected in the literature. So in the multifactorial spectrum itself is during this different instance fluctuates or wobbles in a periodic manner. Now during thermoacoustic instability, what happens, there is a large scale roll-up and small scale roll-ups. So the small scale roll-ups contribute to large scale roll-up, and that is suggestive of collective interaction. So we extract the contours and do the spectrum. But before we do that, we can see that the primary difference between this image and the real image is that the flames fill the space through the phenomena of collective interaction. So during thermoacoustic instability, the flame is actually filling the space. That means it's actually getting a higher fractal dimension. So you can see that the capacity dimension is having a high value and oscillating, same with maximum, most dominant singularity, and the multifactorial spectrum is actually oscillating. I'll show you a movie with that. So the multifactorial spectrum oscillates periodically at the time scale of acoustic pressure oscillations as this coherent structure emerges and rolls up. So if I play this movie, so you can see that as the flame comes and rolls up, the multifactorial spectrum moves to the right and it also goes up. That means it's more space filling. That's what it means. So periodic oscillations, there is periodic oscillation in the multifactorial spectrum, and this manifests as periodic oscillations of the acoustic pressure and heat release rate. So the periodic oscillation multifactorial spectrum possibly results in the loss of multifactoriality in the acoustic pressure because that's periodic. So next I want to look at spatio-temporal analysis using time-varying complex networks. So we have heat release images and we look at acoustic power. We take the product of P prime and Q prime, and we see wherever P prime, Q prime is positive, that is a acoustic power source, and wherever it's negative, that's a power sink. So what we do, we look at the neighboring acoustic power sources, and if neighboring power sources are positive, then we connect them. If they are both not positive, then we don't connect them. So that's how we construct the network. So we construct weighted acoustic power network at each instant of time, and we only consider the neighboring acoustic power sources for the network construction. So now we have high-speed images, so we construct time-varying weighted acoustic power network for a given control parameter. We also construct time-varying vorticity network from the simultaneous vorticity measurements, and if two neighbors are either positively connected, or either positive, having positive vorticity, or if both are having negative vorticity, we'll connect them. But if one is having positive and one is having negative, we do not connect them. So thus we constructed a weighted vorticity interval. So weight is the average of these two values. So now this is for combustion noise, or the aperiodic part of the signal, low amplitude aperiodic oscillation during stable operation. And we can see that during the occurrence of combustion noise, acoustic power production occurs in small fragmented clusters. Now, during thermoacoustic instability, the acoustic power production occurs in large clusters. I want to draw an analogy with this nowadays because the coronavirus, there's a lot of discussion about how the virus spreads, and initially things are scattered, but then as people get more and more people get infected, then they have clusters of population where the contagion is, the virus is present, and then when these clusters get large, that's when the infection rate goes up and mortality rate goes up. So there is clearly an analogy here, because during thermoacoustic instability, the acoustic power production occurs in large clusters. And what happens during intermittency? So during a periodic epochs of intermittency, acoustic power production occurs in small fragments, and during periodic epochs, you see large clusters, but of course they are not as large as during thermoacoustic instability, but still they are large clusters. And during the growth phase, you see nucleation, coalescence, and growth of acoustic power sources. So this is a standard way with which oscillations grow or any instability grows, and this is clearly similar to how the disease spreads with nucleation and coalescence and growth of clusters. So something like that happens here. And when during decay of oscillations, we see disintegration of large clusters into small fragmented clusters. So we have unraveled what's happening in the spatio-temporal dynamics during the onset of instability. And here clearly there's a coupled hydrodynamic and acoustic interaction. We can also get a lot of statistics. For example, link density quantifies the number of locations at which acoustic power production happens. Size of the JN cluster, which quantifies the extent of spatial coherence of acoustic power production. Number of clusters quantifies the spatial coherence of acoustic power production. So we choose a region of interest here. This is where the coherent structure forms, all the action happens. So this triangles show the RMS value of acoustic pressure. So that stays low and then rises. But even as it is staying low, in these points you can see that the link density is changing, is increasing. Size of the JN cluster is, even before the amplitude has gone up, the JN cluster is starting to form, and the number of clusters are coming down because you are getting bigger and bigger clusters. So even in there's some kind of dormant phase here where a lot of action happens in the spatial domain, but it's not reflected as pressure until much later. Again, similar to the disease spread, we see nucleation, coalescence, and growth of acoustic power sources. And perhaps onset of thermoacoustic instability can possibly be viewed as a percolation-like phase transition, but more work needs to be done for it. So next we want to look at smart passive control, and we can use spatial weighted correlation network from the velocity field. So we have the PAV data, and at each point we extract the time series corresponding to the velocity fluctuations at that point for different instants of time. And so the turbulent flow is divided into grids. People who are familiar with PAV, they will know that we have grids, and in that we find the velocity. So each of these cells is a node of the network, and we can construct a spatial correlation network by using a Pearson coefficient. So two nodes are connected if the correlation coefficient is above a threshold of 0.5, and this correlation coefficient itself is considered the weight of the link, and we can actually compute what is called network centrality measures, such as node strength, which measures the strength of the interaction of a node with neighbors, or a weighted local clustering coefficient, which measures how well locally the nodes are clustered, or what is called weighted closeness centrality, which tells the speed of information propagation. I won't go into detail, but you can plot these measures, any of these measures. This first column is a stable operation, second column is intermittency, last one is thermoacoustic instability. You can see that with all these measures, there is a region here which seems to be having very high value of the centrality measures, and this is a critical region. So perhaps if we would disturb this critical region a little bit, we could perhaps kill the instability. So that's the hypothesis. So typically people use active control and passive control for controlling instability. Although active control has been demonstrated in the laboratories, it's really not used in industry. Passive control is what is used, but the problem with passive control is it's usually done by trial and error, which is quite costly. You have to try lots of things, but is there a smart way to do it? So here I want to show a movie which will explain my thoughts. So these two guys are fighting with each other. So here this guy hit a particular pressure point and then he froze. Okay, so this is a technique in martial arts. This is a martial arts called Kalari from Kerala. So there are certain pressure points which are very sensitive. So you don't have to use brute force. Just a little pressure there can freeze the opponent. And so here is the pressure point of a combustor. If we can inject microjets there or just redistribute the cooling holes such that you disturb this flow field here, the aerodynamics here, then you can actually suppress the instability. So this critical region which we unraveled using this network is actually the optimal location. So what we did is to inject microjets, and we found that the amplitude of instability came down. It actually came down to the levels of stable operation. So if you inject it here, and if you inject elsewhere, it doesn't come down. So we're very happy with this result. So this is like a smart passive control. And so the critical region actually, when you inject, this critical region actually disappears. That means we are not allowing these clusters to form, and that's why the instability doesn't happen. The instability happens through this nucleation and growth phenomenon. And so we are the coherent acoustic power production centers, large clusters are destroyed as we increase the injection rate. It's actually very slow, very small amount actually we're injecting, but it's killing it. So I have seen doctors doing cardiac ablation and so on. And recently I attended some conferences where I found that they're using similar techniques to find out which are the regions that they should ablate, using techniques from nonlinear dynamics and complex system theory. So perhaps these kind of techniques could be used in thermoacoustic instability as we have demonstrated. One more technique I want to talk about mitigation is amplitude death. I don't know if young people know who they are. On left is Khrushchev, Communist Party chairman of Soviet Union in the 1960s, and here is this is Khrushchev and this is Kennedy, and this is supports they are having the nuclear button. They want to press it, and there's a Cuban missile crisis. I think the young people may not remember this, but some of the older ones here might remember this crisis. So I just want to show. So what I'm trying to say is both are very powerful people, but when they interact, when they're coupled together, nothing happens. So we had all these nuclear weapons, but word didn't go off because I don't know, they balance each other. So I want to show a picture. I will show two candle oscillators. I haven't played the movie yet, but when I play the movie, you will see that this, if you look here on the left, you will see these oscillators in phase, and here you will see them anti-phase. But in between, I am adjusting the distance between them. You see these are very close, these are somewhat far, and at the distance in between, both will stop oscillating. So let's see this. So you can see that here the oscillators are oscillating in phase, here they are oscillating out of phase, whereas here they are really not oscillating. It's not a still movie, they are standing there, but they are not oscillating. So this is the concept of, so the oscillator is synchronized, and at some level of coupling, the oscillators can stop oscillating. So this is called amplitude death in nonlinear dynamics. So can we use this concept in thermoacoustic? So we demonstrated it with a Reiki tube. So I got into this Reiki tube after reading Maria's thesis. The young students have not read it. It's a very interesting thesis, and that really inspired us to work quite a lot on Reiki tube. And we also were inspired by her model, and it was very fruitful. We learned a lot of things, although there's no combustion in it, but really we can learn a lot. So there are two Reiki tubes, not exactly identical but close. And we have a connecting tube, which the physicists would talk about coupling. So this is the tube which couples, and there is an extension duct with which we can detube. We like to have small detubing to stop the oscillation. So we can get the phenomena such as amplitude death, partial amplitude death. Amplitude death is in both the it will stop oscillating. In partial amplitude death, one will stop oscillating, the other will oscillate depending on the coupling. So these are phenomena which nonlinear dynamics predicted, but we can see them come alive in thermoacoustics. So here is a case where you see a small suppression. Now here we detune a little bit change. One of the frequencies is 7 Hertz, and we completely quench it. Or here one is quenched, one is not quenched. This is partial amplitude death. So this could be relatively easily incorporated in a CAN type combustion gas turbine engine, because there are a lot of cans and there is already a crossfire tube, which actually this purpose is to make sure that the flame don't go off and flames can spread. So if you could probably tweak the crossfire tubes, you could get amplitude death in CAN type combustors. I'm coming to the end of my talk. So just to summarize, the beginning has been made to study the spatio-temporal dynamics of thermoacoustic system using the frameworks of synchronization theory, complex network, fractal and artifact analysis, and pattern formation, to name a few. I wish to say that the study of the spatio-temporal dynamics is indeed the next frontier of studying thermoacoustic instability. And the tools in nonlinear dynamics and complex system theory are now really well developed that it doesn't make any sense not using them and sticking to all the old ways of doing thermoacoustics. We really don't pay any attention to turbulence, but I think the complex system theory can really help deal with the whole system in its fully holistic manner. And complex systems are known to display pockets of order amidst disorder. During intermittency, we find bursts of high amplitude periodic oscillations which correspond to pockets of order. Scattered amidst epochs of low amplitude periodic fluctuations which corresponds to pocket of disorder. Synchronization theory revealed that during the occurrence of intermittency, we saw chimera states where pockets of order coexist with pockets of disorder. So these are classic telltale signs of complex systems. And during the emergence of order, large coherent vortices emerge from the collective interaction of small vortices, and I want to emphatically say that hydrodynamics plays a very big role here. Now, one thing that is not investigated in detail is the role of preheat. That is something that we are doing now. So we can try to use complex system theory to help mitigate the thermoacoustic instability. So one way is to look for precursors and avoid the instability. Another technique is the synchronous quenching, where we force the system, but it's not active control. We are open loop forcing. We are forcing it at a frequency away, and we can stop the oscillations, or we can do amplitude death, where the two or more systems are unstable, but we connect them and we can stop the oscillations, or this smart passive control which I just demonstrated. So transcending the it's all about transcending the boundaries between maths, physics, and engineering, because these complex system theory has been developed really by people from all kinds of subjects: social sciences, medicine, physicists, biologists, electrical engineers. So I think if you bring in this, and we should transcend the math, physics, and engineering boundaries which are man-made, and improving your understanding of thermoacoustic instabilities and controlling them will require the application of the latest advances in complex system theory. And to achieve this, groups that do laser diagnostics, such as Yanis in Imperial College or Stuttgart, DLR, and groups that do LES, like Wolfgang and so on, need to work together with researchers who work with complex system theory. And we also face a new frontier in translating the lessons learned from complex system approach to design and engineering practices. It's one thing to write papers in physics, but it's another thing to translate these lessons into design practices and engineering practices. And I would say the real test for complex system theory is its ability to provide something useful to the designer to mitigate thermoacoustic instability, and to the engineer in the field to evade it. And complex system theory itself needs to be advanced to accommodate the complexities of turbulent flow, because normally physicists, when turbulent flow is much more complex than all the complexities that physics deals with. So I think our topic is something which really pushes the theory to its best, and it needs to advance further to accommodate the full complexity of the turbulent flow. And this is indeed an exciting prospect. So I would say, fasten your seatbelt, exciting times are ahead. Thank you. Perhaps you could turn the loop on.
Thank you very much, Sujith, for a wonderful lecture. I suppose you're happy to take questions?
Yeah, I'll be very happy to take questions.
Okay. Any questions? Can I ask a very simple question? You showed the two candles, and depending on the distance between them, they are either oscillating in synchrony or dead or oscillating in antiphase. Can you do that with any normal candles?
Actually, you need a special candle oscillator. So I think the simplest way is to bind 3 candles together and becomes a candle oscillator, or 3 or more candles. So we need 3 or more wicks to make this oscillator. So we have some papers on it where we explain how to make this, and it's quite simple to make.
Right, and I understand that was the picture on your Christmas card.
Yeah.
Very nice.
It's a very simple toy with which you can learn lots of things. Actually, we learn to get AD amplitude and radial tube by playing with candles.
Okay, and that's a diffusion flame, so a completely different type of flame.
Right. So the key thing, if you listen to physicists, they would say that during phase transition, systems that are completely different, they will behave close to the transition, they all behave in the same way. So I find that very true with the dynamic transitions also. Systems which are very different but close to the transition, they all behave in the same way. So I think that's the foundation of renormalization group theory and so on. So I find that to be true in our systems also. And also in the morning I showed that aeroacoustic systems, aeroelastic systems, thermoacoustic all behave in the same way. So I think there's underlying all the transition and turbulent flows, there seems to be some really deep unity. Although the physics is different, they all conspire to make things happen in the same way.
Okay, thank you. Any other questions? Yeah, Ganesh has a question.
Sujith, you showed that you do this microjet for control.
Yeah.
Do you inject only air, or air and fuel, or what do you inject?
I injected a little bit, a small amount of air. So I think that in a real gas turbine engine there will be some cooling air available, so we can redirect it towards these critical regions. Maybe you can stop those two.
But then you change locally the air to fuel ratio.
Right.
If you put only air.
Right. So in this case, it should have. So we put very small amount of air, and this should have actually made the engine more unstable if you looked at the equivalence ratio, but it actually made it stable. Now, I'm not advocating air jets as any specific form of passive control. I'm saying this is the location. I use air jets to demonstrate that if we can disturb this location in some way, we can stop the instability. I'm not advocating air jets, there may be some other way, but this is the region which you have to disturb. So you could possibly have small delta wings which create vortices which impinge here, so that you don't have to change the equivalence ratio. So what I'm trying to say is, where should you direct the passive control at? So this is the critical region. So there's no point in hitting all over the place. You use whatever technique you have to disturb this region.
Yeah. There's a question from one of the fellows, Simone.
Yes, please.
Yeah, can you hear me?
Can you come forward and speak?
Yeah. Hi. Hello. I'm interested about the method with which you actually computed the region that was most effective in the same example that you were just talking about. And is the kind of method even applicable to computation methods, or do you know if it has been already applied to numerical methods?
No, I think ours is the first time we did this, but and we have a recent paper in Euro Physics Letters, and but definitely it can be applied to LES data, and I think that is a real application. But I like to believe external data, so that's why we did experiment. That's the first thing. Second thing, I didn't have any LES data, but ideally, if I were a gas turbine company, I would like to engineer in a gas turbine company. I would like to do this on LES data at the design phase, so that I know I can check if there are any critical regions, and then I can redo the design so that they can be got rid of. So definitely it will work. These techniques, they don't really determine, you just need some kind of field variables. So you can obtain data from LES computation. Only thing is the computation has been faithful, so it should really replicate the true physics, and it should have all the features of the explorer data. It should work.
Okay, thank you.
Okay, any other questions? No? Oh, yes, two questions now. Want to go ahead? This is Nikhil. One of the qualifiers asked.
Good evening.
Hello.
So you showed the plot of acoustic power generation in the combustor. It was
Yes.
just downstream of the bluff body, and is it replicated also in the near port boundary conditions and also the exit because there's acoustic power loss in the walls? It's the same phenomenon expected.
No. I'm looking at the plane region where power is generated. That's the only place where power is generated. So during the stable operation and intermittency, within the plane region itself, power can be absorbed. So I'm only looking at those regions because that's where the power is coming out of the system. So basically what we do is get chemiluminescence images and using that, which is going the heat state, and trying to use that to compute the acoustic power projection. So I'm not looking at the exit where acoustic power is lost, etc. I'm looking at the reacting flow region where acoustic power is produced. So it is the only region where power is produced.
There's another question from Shai. Another question.
Yeah, I had one question. You said you can use the same logic for aeroacoustic responses. So, in that case, would you consider the acoustic volume velocity and the pressure? Or instead of the heat release rate, would you consider the acoustic velocity, volume flow velocity?
I would look at the acoustic power production, perhaps like Hose integral or something.
Okay. And in that case, do you think like the locally gapping thing would also influence in a similar way?
I guess so. I think so. But we have to do it to see.
Yeah, definitely. And what literature?
It will be, but there it will be U dot omega cross acoustic power production would be acoustic velocity dot omega cross P. So that is, I think, the Hose power production term. So I think we should compute that on your simulation or experiments. But in the experiments, this would mean doing high resolution PAB images. In high resolution chemiluminescence is easy to get, high resolution PAB images is not that easy to get. But if you are doing CFT, it should be no problem.
Okay. And what literature would you recommend to begin with if you want to study about the Earth's exponent or
There's a paper I have written, which is Nair and Sujith 2014, and it's in Journal of Fluid Mechanics, and that gives reference to some of the important papers in the literature. Elan, which I cite there, so I think those two, if you read, you should be able to do it.
Okay, thank you.
Okay, any other questions?
think that you have an advantage by being in India to be able to do more combustion than we can do here. So, for sure, I agree with you. Being able to get the funding to do the experiments, at least in UK, at this moment, is hard. So, if this is a problem to do that in India, I would be happy to do it there.
All right.
But yeah, let's discuss.
Yes.
Okay. Any other questions from the audience? No? Any other questions from you, Sujith?
No, I'm just curious whether, because I couldn't really see the reaction, but I think everything I'm telling is probably very new to them, so it's probably quite hard to follow. But I do agree that it's a very difficult topic, and but all I'm hoping is that if you could get a flavor of what can be done with it, then you would be more. I hope you would be motivated enough to look into it and read a lot and try to find out, because maybe we don't have to do new experiments. Maybe already experimental data exists with people who have been already doing these things, and then probably we can learn more from all the data that is around the world available. But I think there is no, my only plea is that it's not an easy subject to do complex systems where you have to learn a lot, and we engineers are really not trained. I'm actually surprised to find that the people who work in physiology and so on, seem to be much more knowledgeable about this technology from physics than us engineers, but it is worth learning it, because there's a lot we can do with it. Because, for example, the medical instrumentation, for example, this heart blood monitor, all it does is nonlinear dynamics and complex system theory, and it can tell you the condition of the heart, how close you are to a problem. So I think, and that's nothing but nonlinear dynamics and complex system theory. So I think it's worth learning it, but learning it is not easy. It's quite hard work, because physicists have done lots of years of work to develop into some subject. So, but it is very exciting. So I would say that I have to work hard. My students have to work very hard to learn these things. But it was very exciting to go through this. So that's my word to the Polka fellows.
Okay, great. And can we have your slides, please, so we can put them on the Polka website, and then our fellows can revisit your lecture.
Right. So can you give me one of days, because this is with I have to the movie, so this is like a gigabyte or something. So I have to make a PDF out of it.
If you make a PDF,
PDF and make it.
yeah, and there's no Russian rule. I'm not going to look at it this week.
Okay. So if you give me some time, I will send it.
That's great. Thank you very much. And thank you once again for your lecture. It was terrific.